So I'm going to record. Okay. So hi everybody. Today we're going to discuss design for test. And again, I just want to say that this isn't as fine-tuned as some of the other lectures, but I hope it will sound like it is. Okay. Just so you should know, Yehuda is in the crowd here, and Yehuda gave a lecture and recorded it and it's on the wiki. And you can see his original. I thought at first to say that it was based on Yehuda's lecture, but in the end, I changed it a lot. But in general, I got a lot of inspiration from Yehuda's lecture. Okay, so just as an intro, what we're going to be discussing today, introduction, then the testing process, design for test, built-in self-test, and a few words about boundary scan, which maybe Tzachi can help us with if we make it there and have time and so forth. Okay, so just to start, we're talking about testing here, but you also know the word verification, which we hear a lot of in VLSI. So what is the difference between testing and verification? And here are a few points about the difference between the two. So verification is what we do while we're designing the chip, and we verify the correctness of the design. We see that what we plan to do is actually what we're going to do according to the spec and so forth. That's verifying the correctness of the design versus testing, which is after we manufactured the hardware, we verify that it actually was manufactured correctly, not that logically it was working correctly. So that's a very big difference between the two things. That's the main difference.
Another term that people confuse, which is validation, which is neither of them.
So validation is what, Udi?
Validation is making sure that you are compliant with the spec. Testing is, in the context of this lecture at least, is manufacturing correctness. Validation is after you have the device, and you validate it.
But you also should be validating during verification.
Yeah, but it's not the same.
It means that your whole system actually is valid. Okay. The other thing is that the next step is that in verification, we do it using simulation. We can use hardware emulation, and we can use different formal verification methods. For testing, we do something very different that we're going to be discussing in this lecture. We're going to be doing test generation. That's something that we run some software that's going to make tests. Then we're going to take that software that we did independent of actual hardware, of having the actual hardware, and then we're going to apply it to the hardware using testers or different test setups. Verification we do once prior to manufacturing versus test we do on every single device that we get. Okay, and the responsibility of verification is that the quality of the design versus the responsibility of testing is the quality of the devices. Okay, so that's kind of a very rough difference between verification and testing. When we discuss the cost of testing, we should take into account a couple of things. So on the one hand, we have the DFT, the design for testability, which we'll discuss in a whole section over here, but that's different hardware and things that we add to the actual chip that makes the test generation easier, and it makes the chip easier to test or even feasible to test. And it costs us basically because we have to add structures that cost area, and it also can hurt our performance. So that's one aspect of testing. The other aspect of testing is the software processes. So we have to generate the tests and so forth, and that's R&D that we have to do. And of course, the actual test itself, the manufacturing tests. So just to understand kind of, and these are numbers that I took from something really old, so basically 15 years ago, but I think they're good enough to understand. So if you take an automatic test equipment, an AT, there's a better known maybe as a tester, one of these big machines that runs the tests. It costs millions of dollars to buy, and it costs millions of dollars to maintain it. So we're talking about a really high cost just to have one of these testers, and we probably will need many of them to do the testing. And the operational cost will be about several cents a second. And if we say we're operating at one tester for 24 hours and it costs several cents a second to operate, that's $1.5 million a year. So we see that the testing is very expensive in the manufacturing of chips.
What really matters and is the testing cost per unit. Eventually, you calculate when you manufacture, you figure out how long will your test run to test a single unit, and this is actually the cost, is a component in the cost of manufacturing, and this is the biggest concern: how much will I pay per unit extra for testing per each unit? So the motivation to make the tests short as much as possible is very high. And much of the time depends on the size of the patterns. So we'll get into that.
Mm-hmm. Well, we're not going to go deep into it, but we will discuss it a bit. Yeah.
Usually you need to, in the early stage of a project, you need to figure out, to estimate. This will take, I don't know, 20 cents per unit to test.
Okay. So what's the cost of not testing? So Yuda made this little thing. I don't know if he copied it from somewhere or made it up, but a defective chip, it's going to cost us a bit. If we already put the chip on a board, welded it on the board and so forth, it's going to cost us more. If we already integrated it into a system with several chips, several boards, etc., and other plastic parts and so forth, that's going to cost us a lot more. But if we already sold it, we're going to get this lady who's not too happy with her computer, and then it's going to be really, really bad for us. So it's the reputation of the company and callbacks and who knows what. So that's really bad. So that's the cost of not testing. The most expensive defect is the one that wasn't detected. And so we should detect the defective parts as soon as possible. Okay. In production testing, that means that we made a chip, we fabricated it. Now we have to detect all kinds of defects, like you can see here in these pictures over here, that may impact the functionality or electrical parameters. Okay. Ideally, we want to check every single node and every single type of failure, which we discuss. We usually can't do that, but we do something that's as close as possible. So here, if we had our whole abstract of our design from system specification, circuit design, physical design, verification, then we sent the tape out. When we get it back, we're going to do the tech testing and the packaging, and then we're going to sell our chip. So that's where we stand in the whole flow of things. So what is the flow? So we have this tester over here. In NX, we don't have currently we don't use a tester, at least. We just do benchtop testing, but I guess essentially it would be a similar type of things. We ran that software before that we built these test patterns, and we're going to discuss that during the lecture over here. We're going to take our wafers or our packaged chips, actually both. We're going to do it first on the wafer and then on the packaged chips. We're going to stick these two things into the tester, and the tester is going to say it passed, then we can sell it. If it failed, then we're going to maybe throw it away and maybe go through diagnostics and yield learning and try to improve the yield and see how we can make our yield go up. Okay, so that's kind of the thing. There are several types of steps that we take when we do production test. So the first one would be wafer level testing. So you can see this picture over here, which is like a yield type of map where we went onto the wafer and we marked bad dies on the wafer. That's an important thing to do because we don't have to pay for the package for the assembly and packaging. After we've done this wafer sort and thrown away the bad chips, then we go and we package the chips, we assemble them, we put the package on, and then we can do all kinds of tests after we've packaged them, such as burn-in, which is a test where, we're going to discuss all these things, but we elevate the temperature and we run it in a high temperature. And then we finally can also do some sort of pass or fail test, and bin sorting. We can divide the chips into what frequency they meet and so forth. Usually we're going to do all kinds of parametric tests that show on a few axes for example, what voltage we run and what temperature we have and what clock speed, and then we show which chips pass and which chips fail, and we call such a plot a shmoo plot. I discussed it with you guys who in last year's course, those of you who did it. So this type of a plot is a shmoo plot, and it's usually what we show for where our chip actually works. So the first stage that we said over there, and maybe the most important, is the wafer sort. So wafer sort, also known as probe test, that's where we actually do the testing on the wafer itself. So it's before we diced the chip or scribed and cut the wafer into chips, and before we went and paid for the assembly in the package. Okay, so it's much cheaper to get rid of a chip over here. So what we want to do basically is as much testing as we can do on the wafer before packaging. I think if I understand correctly, in the past you couldn't do that much. You could go and measure like that you didn't have shorts or opens on the different types of pads and things like that. They have gotten to much better levels of testing where nowadays you build one of these probe cards, which is a really, really expensive board, very, very expensive board.
Probe cards. I've been testing with probe cards, I don't know, 30 years ago.
Did they test the whole test though, 30 years ago?
Yeah. It was even easier because the packages were, the density of the
dies was small.
Dies were, and the pads and so on. Actually, today, and you do not always do, it's economical, it depends what is the cost of the package. If the package is very expensive, then you really want to save the package. Sometimes when the yield is extremely high and the package is not that expensive, you skip wafer sort.
Okay.
But it's a economic decision.
So in any case, with the wafer sort, so you build one of these probe cards, which is very, very expensive. Udi, how much does a wafer, a probe card cost?
It costs 100K for 50 to 100K. It's very expensive.
You have to build one of these per each different chip. It can't be generic, basically. Inside, if you look at it, one of the ways that they make it is what they call cantilever pins. So they have these mini pins that go, and in the end, they touch the pads on the chip itself. And in fact, one of these things, from what I understand at least, it can either touch one chip and test one chip, but you can make them so they test up to about 16 chips at once. The actual probe card goes down usually now on a 12-inch wafer, but then this thing moves between the dies that are on the wafer. It takes less time to go and make the actual like touching it and sticking on it really well. There are also different things that you draw onto the wafer that help the wafer prober be able to find the exact place where it should position itself to connect to the pads. So this is the type of thing that's done in the wafer sort. Okay. Anything else, Udi?
The guys who develop much of this technologies are in Rehovot. What's their name?
Applied Material?
Applied, yeah. They do a lot of stuff, but also...
But is Applied Israeli, or it just has a big R&D center in Israel?
No, they have a huge center there.
Including, did Odem ever show up? Her father works at Applied.
Right.
No, she didn't come. Yeah, okay. So what kind of tests do we do? There are all kinds of DC tests. So we contact the pads and measure their resistance. We measure the max current at the worst case temperature for a power consumption test. We measure if what's called an output short circuit test, where we measure the current driven when the output is circuited to see how much it can drive. The output drive current test, we measure the current that's driven for when it drives a 1, when it drives a 0. Threshold test measures like the threshold voltages of the input pads to see if it knows that we're driving a 1 or a 0 and so forth. So those are kind of DC generic type of tests for the IOs. And then of course you have the AC parametric tests where you're going to measure the rise and fall times, the setup and hold times for the IOs, and the propagation delay of different things that go out of the chip. But those are the kind of basic electrical testings that you're going to do on the IOs around the chip. When we discuss, I mentioned before, there's burn-in or stress test. So this is a process where you take the chips, put them in an oven that has a high temperature, say 125 degrees. This applies stress to the device, and then you run it for a long time. It's supposed to simulate what would happen if you would run the chip for many like years. And the two reasons it's done is this thing on the right that's called a bathtub curve. So it's an important curve for engineers to know in general, but it's very common in the ASIC world. What happens is that when you take a chip, a high percentage of chips, not a lot of chips, but out of all the chips that will ever fail, a high percentage of them fails very early on during use. That's called infant mortality. Then you have a lot of chips that just work for a long time. And then after a long time, due to aging and so forth, you get chips that start to fail, but that's down the road, and it's less of a problem because often the product is already old, and okay, I bought a TV 10 years ago, it died, I'll just buy a new TV. But if I bought a TV and a month later it dies, I won't be very happy. So we want to get rid of this infant mortality. So why does it happen? There are different chips that have like all kinds of devices that are going to break real easily. They had some connection that was really weak, so it worked, but once we put some stress on it, it's going to break or something like that, and then the whole chip won't work. So that's what we try to do with this type of a burn-in test. There's something called freak failures where chips will all of a sudden die, but infant mortality is like the main thing we try to get rid of with these burn-in tests. Okay, now this we know pretty much from the undergrad course, but when we look at die yield, so die yield is the number of good dies divided by the number of manufactured dies, and we want to get this as high as possible. One of the modelings of yield is this 1 plus dA over alpha to the power of minus alpha, where D over here is the defect density. So that's the average number of defects per unit area. Okay, and that's kind of a parameter of the process, and it's kind of I guess it's a bit of a constant. Maybe it goes up as we go to more scaled technologies with all kinds of different more complicated process steps, but it's kind of a constant. Okay, then we have A is the chip area, and we know that the chip area is very costly, and the larger the chip, the lower our yield. And then there's this clustering factor, which says, do these failures, like I don't know, a particle of dust or something, is it happen completely independently? There'll be one over here on the wafer and one over here, or that several will be in the same area. And actually, it turns out that usually there is this clustering. They're not completely independent of each other, and that actually helps the yield. So just as an example, if this dA equals 1 and the alpha is half, we'd get a yield of 0.58, which is a really bad yield. But it really, again, depends on so it depends on the chip area, of course, because as I said, the defect density is something that's I think a constant per process, at least per process during whatever point of its life it is.
Depends also.
Yeah.
It depends also very much on the nature of the die, if it's how much memory is there, and if the memory has redundancy, because memory with redundancy is effectively zero area, because you can usually save it. The chances that there will be more than one failure in the memory are not high. So those create more complicated formula.
Okay, that's a good point. So what the model that we developed in our undergrad course is that the die cost is basically the wafer cost divided the die per wafer times the die yield, and the IC cost is the die cost plus the testing cost plus the packaging cost divided by the final test yield. So this die yield would be the wafer sort yield. So anything you can throw away at the wafer sort will affect the die cost. If you can't throw it away at the wafer sort and you do another testing, you usually always, in any case, even if you did a complete test during wafer sort, you do another test after packaging to see that the package was connected okay, that nothing happened during the assembly and so forth. So you'll throw out some more dies, but this you really want to be as high as possible, or else you pay for the packaging extra. And the testing, so I guess that actually you would have to have in the wafer cost also a testing cost factor and so forth. So these models are very simplistic. There's also something that they call defect level that the yield guys talk about. That's the ratio of faulty chips among the chips that pass the test, measured in dies per million. Okay, so this means this is like false negatives, or so a chip passed the test, it was sent out into the field, and it actually came back for a failure. And you should never have, as a rule of thumb, any product that has a defect level that's above 500 DPM. So there's also a model for that, that the defect level is 1 minus the yield times 1 minus the number of faulty chips. Anyway, so that's not a model. I guess that's a formula for the defect level. But you should try to have this defect level as low as possible. You really shouldn't have many chips that come back. So that's a generic introduction. Okay, and now we'll go into the testing process. So there are various. Now we're talking about more like how we approach testing a chip. Okay, we had the tests that I said before that are just checking the basically electrical properties of the IOs and how they work and so forth. But we have most of the chip is inside, and we wanna test it. So this chapter is about how we approach this type of thing. So there are various processes that we're going to have to talk about that enable us to do this. The first one is called fault modeling. Okay, that's to abstract the physical defects and define a suitable logical fault model. Okay, so we're going to have to make some sort of abstract representation of what if a fault is in the chip. That means that whatever we're going to do, we don't have to generate every single type of test that we can ever come up with. We have a limit, we have some sort of scope that we have to deal with. So we'll discuss that in depth in a minute. Test generation, after we have a model for the fault, we have to develop tests that we can test if these faults happen. So given a circuit and a set of faults F, we want to determine a set of test vectors called T that detect all the faults in F. Okay, so we need to have these test vectors, these patterns of ones and zeros and who knows what, that they're going to tell us if there was a fault in our circuit or not. Then we have to run fault simulation. So we have a circuit, we have the faults, and we have a set of test vectors. We know what kind of faults there are going to be by the fault model. We have a set of test vectors that we got somehow. Now, or just even one vector, let's say, we have to, the fault simulation means tell me which faults are going to be tested by the vector that I just gave you. That's called fault simulation. Finding what faults this vector tests. Again, everything here, don't worry, we're going to go over it, each one of these a couple of slides. And finally, we have this thing called the DFT, design for testability, which means that we're going to make some design rules that if we put them in the circuit, then we can actually test it, or else we're not going to be able to. Okay. Some terminology. So defaults, faults, and error. Defects, faults, and errors. They're basically three ways of saying the same thing. The defect is the actual physical phenomenon. So the defect is the unintended difference between the implemented hardware and its intended design due to shorts, opens, and it can be in manufacturing, or it can be throughout the lifetime of a device through aging or whatever. So the actual problem, the physical phenomenon, is called a defect. But we don't really care about the fact that there was a physical phenomenon. We care about what it does. And that we usually bring an abstract representation of it called a fault. So a fault is a model of the influence of the defect on the circuit operation. We're going to be discussing most of all what's called a stuck-at fault. So that means if we short a certain node to 1, to VDD, it's going to be stuck at 1. Okay, so the model is, it's not we had some sort of piece of metal that caused a short circuit between this net and that net. No, we have this node is stuck at 1. that's our abstract representation of the defect that happened because there was something wrong during this and that step. Okay, so that's the type of thing that's a fault. So it's an abstract representation of the defect. And an error is the actual result of the fault. So we had a result, then we get an incorrect circuit response. We get the wrong output signal because there is a fault. An error can also be because we made a mistake in the design. But hopefully our verification was able to catch that. We're talking here about an error that is caused by manufacturing or again, aging type of problem. So those are three words that are often commonly used. They can be interchangeably used, but we're discussing faults in this chapter of the lecture. So just some interesting things, like different types of defects can cause the same fault. So we see on the left here, we see the same circuit, right? And in one of the places we have an open circuit over here on this piece of a horizontal line, and it causes some sort of a fault. But here we have an open circuit on the red on the vertical line. So these are different defects. One of them was in this layer, one of them was in this layer, but the fault is exactly the same. So we don't need to check basically every single type of piece of metal, maybe if it got ripped up or not. We can make a model that catches all of them and check the fault. If there's no fault, then we know that our circuit's okay. Okay. Also, different types of faults may cause the same error. So in this case, we have a stuck at 0 error on this NAND gate, and this stuck at 0 error will cause a 1 to be on this node. Here we have a stuck at 1 on the OR gate, and that will cause a 1 to be here. And it doesn't matter if we had the stuck at 0 error here or the stuck at 1 error here, fault here. Both of them would cause a 1 at the OR gate, and in the end, the output would be stuck at 1. So these are, one of them had the fault over here, one of them had the fault over here. In the end, they caused the same error. But what we're going to actually do is figure out if we have a fault in any of these places and not just look at the errors that could happen that we can see basically in the end. But if we can propagate the error out, then it's equivalent for us. So the question is, I discussed this abstract thing, this fault model. Why do we need such a thing? Okay, so the problem is that the number of physical defects in a chip is really big. So we saw that each piece of metal can have an open or a short, or different types of weird things can happen. And I think it's actually, it's infinite, the amount of things that can actually happen and what you can discuss. So we have to go, and we can't count it. We can't analyze all of the possible physical defects. So what we do is we try to take a whole set of these types of physical defects and give it one name, one abstract representation, and hope that it actually, there's behavior that is common to all these different types of things. Does not necessarily 100% cover equivalence between the things. So again, the fault model, it abstracts away physical defects into some sort of logical model that we can work with, and that drastically reduces the number of faults to be considered. Okay, it enables test generation and fault simulation. It enables evaluation of fault coverage and comparison of test results. So everything we do here is only enabled by this fault model. So in this case, we had this inverter over here. It could have a million different things happen, but in the end, whatever happened here that caused the output to be shorted to 1, we just said this node is stuck at 1, and that's our fault. But it covered many different things that that could have happened in this inverter. Okay. Everybody understand what a fault model is in an abstract kind of way? Any questions? Okay, so let's see. So fault models can be done at various levels of abstraction to trade off accuracy versus the number of possible faults. We can do it at the behavioral level, stick such a fault into our RTL code and see what happens. We can do it different ways. A geometric model, we can put faults down here and so forth. We're going to do it in a certain place, which we'll see. So there are some commonly used fault models, and the first one, which I already mentioned and that we're going to be basically only talking about, is called the stuck at fault. So it says that all failures cause a node to be stuck at 0 or 1. Okay, so we're going to assume that if there's a fault, it means that we have some sort of a short that either is going to cause a node to be at a 1 or a 0. It's a static model, which means that it's independent of technology. It doesn't have anything to do with the speed, with the timing of our circuit. It's not this dynamic type of a model. It's completely static. It is not a real model, okay? It's something that it covers I would say a small percentage of the actual defects that are there, but in practice, it works really well. It shows a lot of the errors and so forth, and it's basically the only one that is in real use, not 100%, because the other one that's quite commonly used is this transition delay fault, and that's newly used. It wasn't used many years ago, unless Udi tells me it was. But there we have where maybe the circuit is functional if we would have waited long enough, but it doesn't meet timing, or something's not working right because of different defects that we have. So they call it a slow to rise or slow to fall fault. There are two types. One's called a transition fault, one's called a delay fault. I'll tell you the truth, I can't understand the exact difference between them, but it doesn't matter. In the end, we have this dynamic fault where we have slow rise or fall times, or a slow path delay. They seem to me to be pretty equivalent, even though the test guys say they're a completely different type of thing. Anyway, so this is the dynamic model. And since it's a dynamic model, we have to test it at speed, which means we have to run our circuit at the actual frequency it's going to run at, or else we're not going to catch these types of faults. And this has become a bigger problem in recent years. And now basically we do have to run this this at speed testing to find the transition and delay faults. It's not enough just to run a static stuck at fault. However, in a lot of ways, you can see the transition type of errors as a sub class of the stuck at faults, or maybe just because they're really hard to find otherwise. So we'll discuss that later, just briefly though. Most of the research and so forth is done for the static type of faults. Okay, other fault models. There are many other fault models. Some of the popular ones are transistor opens and shorts. If you guys would talk to some people in our department, they discuss like this type of bridging fault where you just decide that a transistor disappeared and you had a short between its input and an output. So these types of faults, they for sure can happen. They make things more complex, especially you can't work at the gate level. You have to go down to the transistor level to do it. And the thing is that in the end, the stuck at fault catches most of the failures. So you get a low defect level, or you don't have many things that don't get tested and so forth. So these are not really taken care of by the tools that we use today. Okay, so I've already written stuck at fault in many different ways. It can be SA1, SA2, SA0, SA1, S/0, S/1. You'll see it on different slides here in different ways, but they basically mean the same thing. So there are three properties that define a single stuck at fault. Okay, only one line is faulty. The fan out, okay, if we have a fan out from a certain wire that breaks into several wires, okay, each one of them is considered a separate fault, and I'll show you what I mean in a second. Okay, the faulty line is permanently set to 0 or 1. Again, it's a static type of fault, and the fault can be at the input or an output of a gate. Okay, so an example, this is an XOR circuit. So it's a XOR made out of several NAND gates. And the thing is that if we take this line over here, it branches out into two lines. So the fan out of this line is double. We could have a fault over here at point A. We could have a fault over here at point D and point C. And those are three separate faults actually, because if one of these wires changes and it's actually at the part of this gate and not part of this wire that's connected between all of them, it would only affect this gate and it wouldn't affect this gate. So that's why we have to take these fan outs and separate them and consider each one of these points as a different potential fault site. So if we take this circuit here, all of these red dots, they're actually potential fault sites that we have to check and test. So there's 12 fault sites in all in this type of a circuit, even though there are much less nodes that we would usually take into consideration in circuit design. And because each of them could be stuck at 1 or stuck at 0, we have a total of 24 single stuck at faults in just one XOR gate that was made out of NANDs. So that means there's quite a lot of faults that we get in a chip that has 100 million gates or something like that. And the amazing thing is that we actually do check 99.9% of them, or as many as we can. So this is what the point is of what we're discussing now. Questions about that? Does everybody know what a stuck-at fault is? If you ask Israelis, they all say stuck-at in some sort of strange way, and I don't think most of them know that it's actually stuck at, like, okay, but they call it like stuck-it or something like that. Right? Udi, what do you call it?
Stuck it.
Stuck it, right? Most people don't know that it's stuck at, I think, in Israel. Okay. So let's see what we have here. So for example, if we just take a 2-input AND gate, there are actually 6 faults possible here. So we could have this node A could be stuck at 0 or 1, node B stuck at 0 or 1, and node, the output could be stuck at 0 or 1, right? But the interesting thing is if we put a 0, 1 at the input here, right? What does that mean? If we put 0, 1, we will detect 2 faults. We should have a 0 at the output of the AND gate, right? So if we see a 1 at the output, that means that that the output is stuck at, either the output is stuck at 1 or input A is stuck at 1. If we put a 1, 0 at the input, right, we should again have a 0 at the output. So if we see that the output is 1, we know that we have a stuck at 1 fault at the output, or we have a stuck at 1 stuck at 1 at the input. So that type of a test that we see that actually, if we stick 1, 0 over here and we see 0 at the output, we know that this isn't stuck at 1, and we know that this isn't stuck at 1. If we put 1, 1, we should get a 1 at the output. If we see 0 here, then we know that either this is stuck at 0, or this is stuck at 0, or this is stuck at 0. And if we look at the faults that we were able to detect with these 3 input vectors, we see that it covers all of these 6 possible faults. So we actually didn't need to do 6 different tests to test the 6 stuck-at failures. We only needed 3 tests. In fact, any n input AND gate only needs n plus 1 test vectors to test all of its faults. Okay. What if we take an XOR gate? XOR gate, that's even better. So with a XOR gate, when you take a 3-input XOR gate, you can actually detect all single stuck-at faults with 0, 0, 0, or 1, 1, 1. Okay? Because if we put 0, 0, 0, our output should be 0. So if the output is 1, we're checking stuck at 1 on the output, or one of these is 1. We're checking single stuck-at faults. By the way, I'm not discussing multiple stuck-at faults. Okay, so we know that it's stuck at 1 at A, stuck at 1 at B, stuck at 1 at C. We checked all of those. If we got a 0 at the output, we know that we don't have a stuck at 1 failure here, here, or here, or at the output. Same thing with 1, 1, 1. We're supposed to get 1 at the output. So if we know we have 1 at the output, we're not stuck at 0 at the output. And we know that this isn't stuck at 0, or this isn't stuck at 0, or this isn't stuck at 0. So that's actually pretty cool. An n-input XOR gate only needs 2 test vectors to test. And that's a lot less than all of the options or testing all of the, so we have basically, again, 2n plus 2. Like, so we have 2 plus 1n vectors. We can check it with just 2 vectors instead of 2n plus 1. Okay, is that understood? Does somebody want me to explain that again? Because this is kind of important. Okay. So what I basically said here is that you can have different patterns that if you look and observe and you see that there is if you applied a certain vector at the input to a circuit and at the output you see either a 1 or a 0, you can know that this failure and this failure and this failure didn't happen. So that's called collapsing. We want to see if we can use less paths than we would actually need to check each and every one of these failures. So the number of fault sites in any Boolean gate is the number of primary inputs, the number of inputs, plus the number of gates, plus the number of fan-out branches. Fault equivalence states that if two faults, F1 and F2 are equivalent, they are equivalent if all tests that detect F1 also detect F2. So if we have a test that detects F1 and we see that it also detects F2, then we know that these two faults are equivalent. For example, the stuck at 0 at the input and output of an AND gate. So we know that any test that checks the test is stuck at 0 here, which would be like any test that checks a stuck at 0 here will also get a stuck at 0 at the output. So if we have 1 0 in an AND gate, we know we're going to have a 0 at the output. That's fault equivalence. And the thing is that we can remove the equivalent stuck at faults and collapse them into a single fault. So there's no reason to test two faults when we know that both of them actually tell us the same thing. So if we take this circuit over here and we look, there's actually, I mean, you can see a list of basic gates like ANDs and ORs and so forth, which faults are equivalent. So you can take it and you can see that this and this are the same, are equivalent to each other, and this are equivalent to each other. So we only need to hold one of them, and we can collapse this by 40%. So we get a collapse ratio. We only need to check 20 faults out of the 32 that are here, and that helps us reduce the complexity of how many faults we have in our circuit. There's another thing called fault dominance, okay, where if we would want to write, again, an algorithm to do this and prove these things mathematically and so forth, there's this thing that if all tests of some fault F1 detect another fault F2, then F2 is said to dominate F1. Okay, so in other words, that means that if the tests for F1 are a subset of those for F2. So here's our AND gate, okay, and F1 is stuck at 1 on this node, and F2 is stuck at 1 on that node, okay? So to check F1, all we have to do is put this at 0, 1, 1, right? If we put 0, 1, 1 here, we're supposed to have a 0 at the output. If we have a 1 at the output, that means either F2 is stuck at 1 or F1 is stuck at 1. But is that enough to test that F2 is stuck at 1? No, we have to test all of these vectors to check if F2 is stuck at 1. But since this is the only test of F1, then we can actually collapse it. We can get rid of F2, okay, because it's dominated by F1. So we don't have to check all of these for knowing F2. It's enough to check just this one. And that's also another good thing that helps us collapse these different faults and get rid of them. Okay, so we just went over very, very, very briefly that the fault model gives us some sort of properties between different faults that go along a gate that show equivalence and dominance, and then we can get rid of them, and we can make the number of faults that we actually have to check much fewer than the actual number of faults because they have this type of equivalence. So that helps us reduce the complexity of the problem. Still, it's a hugely complex problem. Okay, and so what we have to do is we have to do fault simulation. So what we said is that given a circuit, a set of test vectors, so we have a different vector like I put in before, 1, 0 or 1, 1 or whatever. I have all these vectors, and I know what the faults are. The faults are stuck at, F is the list of faults, right? Stuck at 1 on this node, stuck at 0 on that node, etc. Fault simulation computes the faults in F that are detected by T. So I say, okay, my vectors are 0, 0, and 1, 1. Which faults do they detect? That's called fault simulation. Okay.
I think the term is a bit confusing.
It's very confusing, but this is the right term.
I think it is fault analysis because
no, Udi.
I tell you what.
I went over lots of books.
I've been doing fault simulation in my life, and what it means.
I know, but I agree that these terms are really confusing, but there's terminology that's like academic terminology, okay? I read this 25 times because it's really confusing. It doesn't make sense. This is the names.
It's fault simulation, but I want to clarify something practically. I don't know what the academic terms are. When you're talking about fault simulation, at least in the past, it means that you actually take your Verilog model, your gate level model. It's an alternative to DFT. What you do, you take your functional vectors or your DFT, but you can also take your functional vectors, start stacking nodes, and I've been personally doing it. Start stacking nodes in your design, and there's also been accelerators for that. And you see if the test is if some test is failing. If some test is failing, then it's good.
So, Udi, you know, they say there's a good question and an excellent question. Yeah. It happens to be that the next bullet is exactly what you just said. Okay, but again, the fault simulation that we're going to be discussing is actually not what you said. The fault simulation we're going to be discussing is figure out which faults are detected by a certain vector. Okay, that's the explanation of the term. Okay, what you said is the next bullet again. It's actually called serial fault simulation, but 1 second before that, there's another term called fault coverage. And that's the measure of the ability of a test to detect a given effect. So fault coverage is the number of detected faults divided by the number of possible faults. So what we want to do, coverage is how many faults were we able, what percentage of faults were we able to detect? And we want to get to 100%, right? We want to get as many, we want to know that we detected as many of the possible faults there are. And the type of flow that we're going to do is we're going to take our circuit description, usually a netlist. We have a dictionary of all the faults that are possible in our circuit. We're going to run fault simulation, okay, with a bunch of test vectors. We're going to see what our fault coverage is, okay? Then we're going to go and we're going to remove faults from the dictionary because we know that our test already found them. We're going to add new tests and see if we can get to 100% coverage. That's kind of, and if you do basically ATPG insertion inside tools, they run this. They make a test vector. They see how many faults are left. They tell you what the current coverage is. They add another vector, run it through, and they keep doing this until they get to a number that's over a threshold, like 98% or whatever you define in the tool, or if it gets stuck. What Udi was saying is that the trivial approach to do this, which is a really horrible way, is called serial fault simulation. And that's to go take every one of the faults in this dictionary, inject it into the netlist, and then find out what the test is that will actually give a different answer than the golden answer. And that's a really tough way. As you said, Udi, you used to do it. But this you did many years ago, right?
No, it's still, yeah, it's a matter of terminology. I mean, as you said, the ATPG is not really, it is analyzing it. It's kind of simulating it. You can call it simulation.
We're gonna get there in a minute how the ATPG works. But this, what you just said, is that you go and you basically search, you brute force search for which type of vector will cause a certain fault. That is an infeasible type of a way to go.
No, it's feasible. The thing is that
if you have 1 billion faults, you can't do that. And 10 billion input vector or whatever, and a billion input vectors, you can't go over for everyone and check that.
Because of the cost of the scan infrastructure. In some cases, you want to minimize the scan chains that you insert. And then you cover it with alternative functional tests.
Okay, I didn't put that in the slide deck. They call that ad hoc DFT.
If you do functional, the thing is that one functional test or very few functional tests provide you with 90% of coverage. And then you can do partial scans. So the way to test whether your functional test is covering or not, there is no other way to do it other than some kind of fault injection, and they're doing it on emulation systems like FPGAs and so on. And I believe that even today, the high performance CPUs, they don't want to spend stages or to make their passes longer just because of scan muxes and so on. So they base much of the tester patterns on functional and self-tests. And then they need to prove that it provides a good coverage. So they have to do some kind of the traditional or the...
However, I think, Udi, that's not what I wrote here as serial fault simulation. It's kind of like a superset of that. So you would write a test, you would simulate and see which faults it covers, and hope that it gets good coverage. But that's not going and actually choosing a specific error and looking for the simulation that will get it.
I've been developing such a tool, so I can tell you, but maybe it's out of the scope. It's still...
In any case, let's say I run a functional test, okay? The functional test, what it's doing is it's applying different test vectors, right? It's applying different vectors to the circuit, so you could relate to each one of them as a test vector, right? It's just the way you generated the test is through a functional test. It's not through random testing or whatever we're going to do later, or pinpointing in a better way. What this is saying is, listen, I want to check the stuck at one fault on this and this net. How do I do it? I take all the different vectors until I find one that gives me I push that vector through. I see it's supposed to have a 1 at the output. Now I change one by one the input pins until I get a 0 at the output. Aha, this one will check it. Let's add it to my test.
The good news that your basic test is likely to
catch a lot.
Cover, I don't know, 80 to 90% of your nodes after 10 cycles. I mean, very few tests. Then
again, but no one's going to do that.
It's done. The battle is later to cover the 10%.
Again, what you're saying is that maybe on a CPU in a certain place where you need the extra little bit of speed, they might do that at an Intel type of place, but in any other ASIC company, they're going to be using what we're going to be discussing later, no?
Standard ASIC is very conservative on the way it is done.
Okay. So again, what I said now, that the fault simulation, one way to do it is to come and take, in a stupid way, say, I want to check this fault, check what happens if there's no fault there, and then change vectors until you see that you get a difference in the output. But that's a really bad way. It would take a long time to find it. The ways that to get towards the algorithms that actually do this, we use, first of all, what's called deductive fault simulation. So here we take each test vector and mark the faults that it detects at each line. We propagate through the circuit in an event-driven fashion. And we'll start with a simple example of a 2-input AND gate to understand what that means. Okay, so we have an AND gate, and we have this vector. So there's 1, 1 at the input to the vector, and obviously the output should be a 1. Okay, so this vector is going to show us if we have a stuck at 0 at the A input. That's the possible faults that we can detect at A with this vector. If we look at A and we see that there's a 0 there, we know that A is stuck at 0. If we look at B and see that the 0 is there, we know that B is stuck at 0. And if we look at Z, what we see is that it's actually the list of faults that we can detect at A. What is this called in English? Concatenated, or with the list of faults at B, and concatenated with the fact that Z might be stuck at 0. So if we look at Z and we see it's stuck at 0, fine, but it's also a combination of these two. So that means that the fault list here for Z that it can detect with this vector is A0, B0, and Z0. So we know that the fault list, we look at the output after we did this type of easy math, and we see that the vector 1, 1, the fault list that it can detect is A stuck at 0, B stuck at 0, and Z stuck at 0. Did you guys understand that probably bad explanation I just gave? It's a trivial example. Does somebody want to ask that they didn't understand? Okay, so then if that's the case, right, let's go to the other option where, for example, we have a vector 0, 1. 0, 1 should provide a 0. So we're going to do the same type of a process. We're going to look at A and say the fault list that we can detect with this vector is, if we see a 1 here, we know that A is stuck at 1. So the fault list for at node A is A stuck at 1. At B, if we see a 0 here, we know that A is stuck at 0. So the fault list that this vector can detect at node B is 0. For the output, again, we have a 0 here. So if we look at node Z and see it's 1, we know that it could detect Z stuck at 1, but it also could detect the logic between these two. However, this is a bit different than the previous case. In the previous case, any change of 1 of A would cause Z to be 0. Any change of B would cause Z to be 0, right? Here, the only time that we're going to have a change in Z is if B doesn't change and A does change. So that is actually called the fault listed A concatenated with the bar of the fault listed B. Okay, that the bar means that it doesn't change. So we want B not to change and A to change, and that has been shown mathematically to be just the fault listed A minus the fault listed B. So we look at A is stuck at 1 minus the fault listed B. We remove all of the faults that are in the fault listed B from the fault list of A, and obviously there is no B stuck at 0 in this fault list, so it just equals the fault listed A. And of course, we have to add to that the fault listed Z. So in this case, this vector shows it's the fault list at the output is A0, Z0. That may have sounded weird. Ask me, please, if you didn't understand. What?
It's not supposed to be A1 in the end?
Yes, it should be.
Okay.
It should be A1. You're right. I did copy paste and I didn't fix it. You're right. That should be A1. Okay, so Elisheva understood this. It was very stupid and simple, but who didn't understand it? Because we're going to use it now. Okay, nobody's speaking up. That means you're either all asleep or it was understood. So let's see a bigger example and why that stupid thing we just did is important. So we now have this vector 0, 1, 0, 1, 0. Okay, and we're going to propagate it through. So the 0, 1 turns into a 1 here, it turns into a 1 here. I don't know if you see my pen. Okay, it turns into a 1 here, it turns into a 1 here, the 1, 1 turns into a 1 here, and the 0 and 1 here turn into 0 here. So the blue is the golden. That's what we should have, right? Now what we're going to do is go each gate and then propagate the gates and so forth to find out what the fault list of Z is. When we find the fault list of Z, we know that this vector 0, 1, 0, 1, 0 is going to detect the faults that we find here, okay? So this is what's called a one-pass type of a system. What we're doing, again, we're simulating the faults. We're taking a vector. We can do it a set of vectors, right? But right now we're looking at one of them, and we're seeing what faults we detect so we can remove them from the fault dictionary. We can say that they're covered. Okay, so let's look. So the trivial thing, right? LA equals, it can find an A stuck at 1. LB finds a B stuck at 0. LC finds a C stuck at 1. LD finds a D stuck at 0, and LE finds an E stuck at 1. So this was very, very, very trivial to get these losses. Okay, then let's look at this NAND gate over here. Okay, so the NAND gate over here, when will it change? It will only change if A goes to 1, but B doesn't change. So that's, whoops, yeah, so that's, so LF, right? The loss function at F is if F is stuck at 0, and LA minus LB, right? Of course, there's no, LB doesn't exist in LA, so it just is A1. So F, with this vector, it finds F0 and A1. For the OR gate over here, right? Again, if we change, only if we keep C at 0 and we change D to 1, it will show the output. So the output is, first of all, it will find if G is stuck at 0. Second of all, it will be LD minus LC. So that means G is stuck at 0 and D stuck at 0. Okay, then we can probably go to the next one. So we have this gate. So what's LH? LH is obviously H stuck at zero. At zero, it will show. But also, it's this AND. So it should be a 1, 1 over here if everything was okay. But if one of these changes, we'll get a 0 at the output. So it's both LF and LG, right? So it's H stuck at 0 and LF and LG. So we go and we take LG and we take LF, we take their lists and we add them over here. So basically at node H, this vector will simulate all of these faults. And then we go to Z, and Z, again, the trivial case is Z stuck at 1. But it's also if LH changes and LE doesn't, so it's H minus E, right? LH minus LE. And we look at LH and we remove from it LE. E is stuck at 1. There is no E in here. So it's just a concatenation of them all. So the bottom line is that the vector 0, 1, 0, 1, 0 was able to detect a total of 6 faults that are written over here. And then we say, okay, in the end, what we would do is we would say, we're going to, in our test, use this vector. And now, out of all our millions of faults that we can have, let's remove these guys, and our coverage is whatever, n minus 6 divided by n right now. Now we'll add a different vector, and we'll remove the faults that it detects, and a different vector and remove the faults that it detects. Is that understood? It's deductive fault simulation?
You might have explained this already, but if you do have a fault in Z, do you have any way of knowing which of them was the faulty one?
I don't care.
Okay.
Okay, so what my goal is, that's a great question. My goal is to find if there is a fault anywhere in the circuit. I don't care which fault it is. You can use some of the methods we're going to do to debug and figure out which fault it is, but that's not the goal right now. And Udi was telling me yesterday that he tried to set up that to debug actually and figure out what was going wrong, but
there are two motivations to find out. One is to utilize it for functional issues, but also for tests. If there is a failure which is repeated all the time, and you're getting the same pattern failing on every chip, on all the chips are failing the same pattern at the same location. Then there is an analysis process where you try to pinpoint the gate or the transistor, which might be causing the issue because maybe it's something in the design and not in the manufacturing, because it's not a random failure. It's happening all the time. Maybe it's some weak transistor or something which looks like a defect, but it is really a design that you didn't catch in verification. So there are, given the limitations that you can't really propagate exactly to the cause because of all the compression and all the deductive stuff, but still you can get close to the area where the failure is caused. And I think there are tools that will tell you, if you give them the pattern that fails and you tell him where does it fail, and it can tell you what are the suspected gates.
So just to add to what Udi's saying here, right now our goal is to go and actually, to save test time, provide the minimum set of vectors that will cover as many failures as possible. Yeah. If we want to do some debug, which is not usually done, and it's for sure not in production when we have good yield and stuff, it's just to throw out the few chips that are bad, then we could go and look for the exact vector that's going to show this failure and not show another failure, or give this vector and another vector which is going to only, if it's going to differentiate, and we're going to only have this failure.
There's a difference between debug and failure analysis, and this is, both of them may require such analysis. Failure analysis means that your chip, you're manufacturing it, you have 80% yield, but the 20% that are failing are all failing. They have some failure mechanism which is repeated. Then you do this kind of analysis, but again, if you have a compressed or an optimized set of vectors, then it would be difficult to find it. Sometimes you maintain a set of optimized vectors, and you also have a set of non-compressed, non-optimized vectors that help you to detect the exact problem.
Okay, but I showed you the deductive way, and that's actually not the best way to do it. But it's the basis basically for what they call concurrent fault simulation. So this is how the algorithms are actually doing this fault simulation, okay? And I remind you the strange name, fault simulation is to find which errors are detected by a certain or a set of input vectors. So actually what's usually used is this concurrent one, okay? And there, we're going to concurrently simulate the fault-free and faulty versions of the circuit for a given vector. And for every vector, every gate, we're going to maintain a concurrent fault list. It's going to show the fault, the input values that would represent that fault, and the output value for that fault. So let's see what this means. We take a 2-input AND gate. Okay, this is our vector, 0, 1, and we should have a 0. Okay. So the possible faults are that A is stuck at 1. If A is stuck at 1, then our input is 1, 1, and our output is 1. If B is stuck at 0, then our input is 0, 0, and our output would be 0. And if Z is stuck at 1, our input wasn't faulty, so it was 0, 1, but our output would be 1. So for each of the gates, we're going to have a list like this. Okay, so now what do we do with a bigger circuit? So we have this circuit over here, and we took our test vector 0, 1, 0, 1. We propagated it through, okay? And now we're going to go for each gate and build that concurrent fault list. So for the first one, again, this is simple, and it's what we did before. A could be stuck at 1. If A could be stuck at 1, then the input is 1, 1, and the output would be 1. So 1, 1, and 1. B could be stuck at 0. The input will be 0, 0, and the output will be 0. And E could be stuck at 1, then the input 0, 1, and the output is 1. So that's trivial in what we saw before. And the same thing we can obviously do for gate G2, just write that thing. Here now we fan into gate G3, and the first step of that is just going to be doing the local response, the same type of thing. We should have a 0, 1 here. Could be that E is stuck at 1. Then we'll have 1, 1, and the output will be 0. F could be stuck at 0, right? We'll have 0, 0, and the output will be 1. Or G could be stuck at 0, so we'll have 0, 1 at the input, and the output will be 0. So that's the local response. But then we have how we propagate these faults down to the end. Okay, so what we do is we look at the problem of G1. G1 should be 0. So we look at which faults would have caused G1 to be 1. And we see that A1 would have caused it to be 1. If A is stuck at 1, then E is at 1. We will have at the input to gate G3, 1, 1, and the output will be 0. So we add it to our list. We look over here. We see also E stuck at 1 will cause E to change, right? So we mark this one as well, and we add it here. If E is stuck at 1, again, we get 1, 1, and the output will be 0. We do the same thing for this. This time, F should be 1. So these two responses are wrong. Okay, so if D is stuck at 0, right, then we have 0, 0. The output here will be 0. So we'll have 0, 0 at the input. If 0, 0 is at the input, we'll have 1 at the output. And F stuck at 0 also. So what we see here, we propagated this, and since this is the output of our circuit that we can observe, okay, we have all this list. We should have a 1 at the output, but this and this and this and this failures give us a 0 at the output. So those 4 failures are the fault list of this vector. So that's just a different type of simulation. It needs more memory to propagate all these things, but it's faster than the deductive fault simulation that we saw before, and for sure more than the serial one. So this is basically how fault simulation is run in different simulators. Obviously, there's probably little changes in whatever in the algorithms, but this is what's going to be done by our design for test tool when it's checking our fault coverage. Okay, questions about fault simulation? Interesting or boring? No responses. Okay. It's hard when I can't see your faces and know.
Very interesting, Adi. Yeah.
Okay, good. Okay. So we discussed again Now, fault simulation. So we know, first of all, we made a fault. Remember, I showed you a few things before. We said there's a fault model. Okay, we saw that. Then we said, if we have a fault model, how do we do fault simulation to see which faults a certain test vector tests? That we just discussed in some algorithms how to do it. And next stage, we have to say, okay, now how do we generate these vectors? Okay, so we saw how to run fault simulation and recognize all the faults that can be detected by a given vector. And therefore, what we're going to do is we're going to do the very obvious thing. We're going to randomly choose a test vector. We're going to simulate it. So we'll collect all the faults detected by the vector, reduce the fault list, right? Remove the faults that this vector already found from the dictionary, and repeat until all faults are detected. But the problem is, and I actually didn't put a picture of it, we're going to have this type of saturating graph. So what's going to happen is if we have, this is our, let's say our coverage, right? And let's say over here is 100% or something like that. And over here is going to be something like 90% or 80%. This is the number of test vectors. So we're going to take the first one and second one, and it's going to go up really fast, but it's going to saturate, and we're not going to be able to get that extra 10 or 20% of our vectors. So what we have to do here is now we have in our big dictionary, we marked off all of these faults, but we still have this fault left and that fault left and that fault left, and we want to find a vector that will actually find them. So how do we go and find the vector for testing a specific fault? And that's a really non-easy and non-trivial type of a problem, okay? The basic approach is to do this: control or excite the fault, observe, propagate the fault through the network all the way to the output, and detect, which is output the value of the good and the faulty circuit. Let's see how that works. The famous algorithm for doing this, rather than going and doing this thing where we would stick in the fault and check all the vectors and find out which vector would actually do it, but actually, again, so what I'm saying now is that our ATPG tool, our automatic test pattern generation tool, is going to make a bunch of random vectors and little by little remove faults from the dictionary and see what our coverage is. And you actually see it when these tools run. It says 10%, 20%, 30%, 40%, and then it starts getting kind of saturated, 81%, 82%, 83%, 83.5% until it gets to whatever its threshold is. But what's happening is once it starts, the randomization starts being less efficient, it's going to go and find a vector that finds a certain fault. And so the first algorithm that came up by IBM, a guy named Roth in 1966, is called the D algorithm. And the D algorithm, it has the concept I said on the last slide. He gave them names that are, you hear a lot of times. They're called fault sensitization. Okay, so you're going to sensitize a fault. What that means, it's a really dumb thing. I'm going to assert the opposite of the fault at the fault site. So if I had a 0, I'm going to put a 1 there, okay? And I'm going to call it a defect or a D instead of calling it a 1, I'm going to call it a D. If I go from a 0 to a 1, I'm going to call it a D. If I go from a 1 to 0, I'm going to call it a D bar. There's a whole algebra of D, D bar, X, and 1 and 0, but I'm just giving you a real simplification of the algorithm here, okay? So this is my circuit, and I'm looking for the stuck at 1 failure over here. Okay, that's what I'm looking for. So what do I do, right? I put a 1 over there, or I put a D over there. Okay, so I put a 1 over here. Let me go back to my laser pointer. Okay, so I say I want to check if it's stuck at 0. So I will sensitize it by putting a 1 over here. A 1 is the opposite of the defect, or I call it a D. Now, what I'm going to do is I'm going to propagate. So the D is over here, and it's also over here because this is the same net as this, right? Okay. The next step, that's a stupid step, this sensitization. All these algorithms usually have these trivial steps that when you see them the first time, you're saying, what, that's the whole thing? Yes, that's the whole thing. Okay. And they use this word sensitize, propagate all the time, okay? So the second one is called fault propagation, which is the forward drive. We're going to propagate the fault to a primary output. So to know that we actually had a fault here, to recognize that there was a fault, we need to get to the output because the output's the only place that we can look at. Okay, so we need to now drive this D So we can see D or D bar over here. If we see D or D bar over here and not a 0 or a 1, we know that we see this fault over there. Okay, so how does that work? So we need to go through this XOR gate, have a D come through it, and this is an inverting gate, so we're going to have a D bar come out. All right? How do we facilitate that? What we need to do now is justify or backward trace. So what that means is we have a NAND gate. It needs to output this, the inverse of this. How do we do that? If we would put a 0 at the NAND gate, we would have a 1 over here. That's not good. So we know that we need a 1 over here. So inline justification, we're going to put a 1 over here. Now we have an OR gate. The OR gate has a 1 at the output. Okay? So we can go and we can decide, because in OR gate, either this will be a 1 or that'll be a 1. We're going to decide, and this is a decision, and there are different decisions that have to be made in the D algorithm, that this is going to be a 1 as well. And putting a 1 here and anything here, we don't care what this vector is. It's an X. We are going to propagate a 1 from G to K. Okay? Now, if that's a 1, obviously, this is going to be a 0. So F over here is 0. Now, since F is 0 and this is D, this becomes a buffer, and D is going to be driven to the output. Okay? But if we have a 0 here, it means there has to be a 0 and a 0 here. Okay? So that means we know that E has to be 0 and C has to be 0. With C, it's not a problem because that's an input. We can control it. But can we get a 0 here? For a 0 here, to ensure we have a 0 here, we have to make B a 0. And there we got our test vector that has no conflict over here. And if we put something 0, 0, 1, it's going to propagate this stuck at 0 fault to the output. So that is the D algorithm that shows us a way to choose a certain fault and find out what the test vector that will propagate it to the output is. Okay, and I simplified this. It's much more complex. In fact, path sensitization is much more problematic. This D algorithm from the 60s is actually really bad. Once you have fan outs and reconvergences, what you're going to do is you're going to have conflicts. So you're going to come to an AND gate, and the output of the AND gate is going to be a 1. So you know that both of the inputs have to be 1. But then you see that some other path that was a reconvergent fan out is going to drive it to 0. So that can't exist. That's a conflict. And in the D algorithm, what you do is you basically have a list somewhere on the side of where you made decisions. It's kind of like going through a maze. I'm going to turn right in the maze. If I get to a dead end, I'm going to go back to the intersection that I made a mistake at and turn to the other direction. But you don't always find a solution. Okay? It also is really a bad way of doing it. And so there are other algorithms that came out. The famous ones are called PODEM from 1981. And the one that's usually used, or derivatives of it, is called FAN, and that's from Fujiwara in 1986. And the rest of them are derivatives of this. This is a common research subject. But the truth is that you cannot find a vector that will find every single fault. In fact, there are different types of things that you try to do in design implementation to stay away from real problematic places, but there can be places in your circuit that you cannot find a fault that will simulate it. Okay, questions about that? Okay, so now we know how to actually do our tests. We know how to set the different vectors that are going to tell us what our fault coverage is. But there's a huge problem which leads us to design for test. So the problem starts in our control theory, and I think that most of you guys learned what controllability and observability are. So the DFT mantra, when we design for test, we need to provide controllability and observability to our circuit. What is controllability? It's the ability to bring a system to any given state, which in chip design means that any desired value can be produced at the internal signals of the circuit by controlling the primary inputs. We can only control primary inputs to our circuit. We have a chip in our hand. The only thing that we can do is put 1s and 0s on the input pins. That's the only thing we can do. Okay? Observability means the ability to evaluate what the current state of the system is. In chip design, that means that any internal signal can be propagated to primary output. Again, we have that chip in our hand. All we can do is look at the output pins. That's our whole observability. And this is a real problem. If we have an AND gate, and we know that there are 2 input pins and 1 output pin, we have full controllability and full observability. We can put anything on the inputs. We can see the output. Our life is good. That's actually true for most combinational circuits. So we have a truth table for the combinational circuits. We can put whatever inputs we want, and we can see the output and know for the most part what's on any internal node or most of the internal nodes. But when we have sequential circuits, it is very untrue. And for many years, they tried to develop all kinds of ways of actually making sequential circuits observable, controllable and observable. That's kind of what Udi was saying, that we try to do all kinds of ad hoc types of design that will inherently make us able to test our circuit without doing all kinds of other things. But it's really, really complex and has very low coverage. And that's why basically when what we know as design for test or scan insertion was invented, it's what basically everybody does, even though it has a huge overhead. Okay, so design for test is embedding testing circuitry along with the functional circuit under test, aiming to alleviate the testing process and to enhance testability. So we're going to actually go and put hardware into the chip that is going to enable us to get controllability and observability, because inherently we have very few pins, very, very many internal gates, and there is no way of knowing what the state is of each internal node. Okay, how are we going to do it? Again, adding control and observation points. That's a really bad way, like putting in all kinds of probes. We can't really do that on chips unless they're test chips from our lab. Scan chains is the main way, and built-in self-test is another way that we'll also discuss. Okay, so let's look at the sequential circuit problem. Okay, so again, they're very limited in their controllability and observability. I want to make a test on a circuit where I put 1, 0, 0, 0 here, and I look at the output and see and I see if the faults that I wanted to simulate were simulated. But how do I get this 1, 0, 0, 0 here? And how do I see if it was a 1 or a 0 at the output? And the answer is, it's really, really, really tough. I have to figure out the state machine that will move everything along inside my circuit and finally put 1, 0, 0, 0 here. So, and then after I run that through the circuit, I get whatever is in the output. I have to find a way to move that so it actually goes outside my chip and I can measure it. That's really hard. Okay, it's almost impossible. So the way we're going to do it is we're going to try and basically remove what I said here, because it takes many cycles to propagate like our data through this cloud and get it into here and so forth. There can be many cycles to drive things into here, and weird things can happen at the different cycles, and I have to control everything to get it here, control everything to get it out. So what we're going to do is we're going to try to eliminate that and basically turn our circuit into a handful, kind of what we did in static timing analysis. If we can look at everything as if it's just a combinational circuit, then we can solve our problem. And that's what scan chain insertion is. So what we're going to do is we're going to take all our flip-flops. These are our D flip-flops that are all over our design, and we're going to replace them. Actually, during synthesis or after synthesis, we have our flip-flops. We're going to basically go and say, okay, get rid of this nice little flip-flop and put in a flip-flop with a mux. Okay, and the mux has some other things that we're going to discuss in a minute. So we changed it, and now with the mux over here, we have this scan import, and we're going to connect the scan import to the output of another flip-flop. So basically, we turned our whole set of flip-flops into a big shift register. So what we have here is we have our D and our Q of our flip-flop, and it goes into some combinational cloud, which is up here, which again, somewhere the output of this will go into a different flip-flop and a different flip-flop, but we don't care, because what we did is we put this mux in the next flip-flop, and we made sure that the Q of this goes into the scan import of this mux. And by using this scan enable or shift enable input, we can choose this red line instead of the operational line. And then this just became a shift register. All of these millions of flops in our design just became one big long shift register. And if it's a shift register, then what we had before in the over here is easy to do, because these were just a shift register. We just shift in 1, 0, 0, 0, then we get the output and we can just shift out whatever is in there. Questions about that, because this is important. Clear to everybody? I know that some of you don't know much about this. Some of you, it's trivial. Okay, good. So that's called scan chain insertion. So how do we actually do the testing? Okay, so this is now our same circuit, but we changed all these guys into scan flops, and now we have turned them into a shift register. Okay, so what we're going to do is we're going to have different phases. First thing we're going to do is we're going to enable scan by taking our scan enable pin and putting it to 1. Okay, that means that the mux is selected on the input that's the shift register input. Then what we're going to do is we're going to have all these clock cycles that are going to shift in through the shift register, maybe 5 or something cycles that are going to drive this 0, 1, 0, 0 or something like that into these guys. Now we have our state, right? We know what the inputs to this combinatorial circuit are. So we know that after it goes through the combinatorial circuit, what our output should be. So what we're going to do now is we're going to disable scan. Now, again, the flip-flop drives this AND gate instead of driving this other flip-flop. This flip-flop drives this inverter instead of driving this other flip-flop, and so forth. We're no longer a shift register. Now we're driving the operational circuit, okay? We run 1 clock cycle, a capture cycle, because now all the data propagated over to here. We do a regular clock cycle. It's going to capture whatever was at the output here. Now we're going to, again, go into the scan enable. Okay, so we're going to raise the scan enable. That means that all these turned into, again, a shift register again. And now we can shift out all the data. And when this comes out of the output, we're going to see what our result was. And now everything we discussed about the test pattern generation, we can do, because we can put in these inputs whatever test we want. And we know what we should see at the output. And by observing it, by scanning it out, we can see what we actually got at the output. Questions about that? That's the important thing that takes up 20% of our chip or 10% of our chip or something like that. Clear to everybody? Good?
Yep.
Okay. Yeah? Somebody want to ask something? Okay. So one important point is that we can overlap the test patterns. So obviously, when we scan out the previous pattern, we can already scan in the next pattern. Because remember, we have whatever, 100,000 flip-flops. They're all now this big shift register. It's going to take 100,000 cycles to shift this stuff in. We're going to need a lot of these test vectors. It's going to take a lot of time. This time, our chip sits on the tester, costs money. Money is something that we want to save. Okay, so so we're going to overlap them by shifting out and shifting in the next one at the same time.
Maybe I'm going to say, but
usually
usually we have multiple. Yeah,
next slide. Next slide.
Sorry.
I mean, I'm not going deep into this because this is actually what one of the things that's especially Mentor graphic specialty. But what we want to do now basically is we want to make these scan chains much shorter because we want to be less time on the tester. Okay, so some implementation considerations, and this is important. And actually, again, this is another thing that really usually you have a team that this is all they do in a company is figure out how to get these scan chains in, because it gets really complicated. But so you can know some of the problems that if we do it in NX or whatever, we'll run into the basic problems. So first of all, the scan clock is typically slower, right? We don't have to scan in things very fast. We don't want to optimize and put big buffers and so forth. So we can do it slow. However, slow means more time on the tester. So we should have an SDC that sets a slower clock, but not a 1 hertz clock. So we still should do it at some sort of speed. Sometimes, by the way, it causes problems in hold because these are shift registers, and shift registers are prone to hold violations. And we have to actually make an SDC with a set case analysis on the scan mode input and fix those types of problems. Okay, so as Udi was starting to say, we don't usually use one big scan chain that connects all of the flip-flops in the design. What used to be done was we would take all of our IO pins that we could use, that we didn't need them, or it's almost all of them, basically, all of our input and output pins, and in scan mode, use them. So each pair could be one scan in and one scan out. And then if we have whatever, 100 pins, and so we can make 50 different scan chains, we can reduce the size of our, if we have 50,000 flip-flops, we can have chains that are only 1,000 flops long and not 50,000 flops long. So that's, and then our tester will have to push in 50 different signals and read out 50 different signals, but that's easier and it takes less time. Okay, so we do lots of parallel scan chains. But there's another problem. We do all kinds of weird things like resets, like clock gating, like all kinds of maybe tri-state buses and so forth. And all of this stuff, analog IPs, memory IPs, all of these things don't work with scan. They don't like them, and they give people a headache. And I'm not going to go into how to deal with them, but in general, Hanan and some of you others have seen that like a clock gating latch has a test enable signal, because this like automatic clock gating we want to put in, we want to completely disable it when we're in scan. So once we go into scan enable, we're always going to pass the clock through. There are problems with, like, for example, what happens when we have multiple clock domains. So we have to make sure that they're all getting a clock at the same time, unless we put different scan chains in different clock domains. So there are a lot of these implementation problems that give people headaches when they're putting them in. And there are different types of design rules that you should keep, that you should make sure that happen. You don't want to do like a reset that's a combinational reset that's going to reset your flops during scan. So these types of things either have to be eliminated by design or be bypassed during scan mode. Okay, one type of a problem that I'm not sure exactly how it's dealt with, but during scan, you're actually toggling the whole design. And usually the chip toggles a lot less of the whole design. It doesn't really toggle everything at once. And that means that there's a rush current that comes in on your tester. And it's not, first of all, the chip might not work because you get this peak power draw. Second of all, it can heat things up, or I don't know. It's a problem, and there is they do have to deal with these things. So you have this problem that there's an excessive current draw during scan because you're artificially actually toggling the whole chip at once. Udi, maybe you know how to give me some insight about it.
Something you need to verify that you can supply this power. It's something to take care of when you do the analysis. I mean, yeah, all the flip-flops are toggling at once. And,
okay, and so some additional uses. So since you have this scan chain running through the design and so forth, you can obviously go and hack it and do all kinds of things like debug with it. As Udi was saying, failure analysis maybe use it for. And also you can do things such as reset propagation and therefore get rid of like reset pins in the thing, but I don't think that that's commonly done, at least not in most parts of the design. So that being said, now we know that we can put these scan chains in. Now we make we want to make it even smaller, and quite a few years ago now they invented something called test pattern compression. Mentor calls it test compress with a big K instead of a C. And basically the idea is that since we need to make a lot of these different types of random vectors, and a lot of the vectors will actually find, you know, similar failure. So again, we randomize which vector we put in. We don't actually pinpoint and choose a certain vector that we want to apply. So let's just apply these random vectors to many different places. And that's basically what test compressing is. You shoot in basically a certain type of a pattern. You have some sort of a hardware that compresses and decompresses it, so you need less cycles to run it in. And you can do many more smaller scan chains in parallel and drastically reduce the size. There are lots of algorithms and lots of things that like the different companies try to do to help you make your tests as short as possible. So nowadays, usually you have this compactor and this decompressor, which will actually help you reduce the number of scan chains, the number of whatchamacallit, the number of flip-flops you have in a scan chain, test your circuit faster, or use a less expensive tester to test your circuit, and so forth. So that's really common nowadays. The other thing is that, as I mentioned before, there's these transition faults and delay faults, which you can't test in regular scan because scan is slow. It's a DC, it's a static type of a thing. And that's not good enough. For example, what happens if you have a certain piece of metal or a certain transistor that was manufactured, but it was manufactured too thin, so the RC is too high through it, and then it's too slow, and you're not going to meet your critical path and so forth. So you need to do what's called at-speed test or AC scan. That's much harder. Okay, you actually need two vectors to do it, and let's see why, kind of. So we have a picture of it here. So what you're going to do is you're going to, at a slow clock, you're going to shift in your data. Then you're going to move over to your fast clock. You're going to take the data that's waiting to be put in. You're going to sample it. On your fast clock, sample the output. Then go back to the slow clock and push it out. Okay? So you need 2 clock cycles. There are ways to do it with 1 clock cycle. They're, from what I understand, not used at all. There are ways to do it with 3 clock cycles. But in any case, because it's not that simple 1 clock cycle, you actually need much more. You have a bigger controllability problem, and it's harder to get high coverage with at-speed testing. Plus, the whole problem with the power consumption is even a bigger problem. So at-speed testing it's done for sure, probably not by all companies. The coverage is questionable, and there's a lot of fighting about it at different types of places like CDN Live or these types of blogs and so forth. They actually complain a lot about at-speed testing. But I know that it's a must to do, but it's not as robust as the regular scan. Would you have anything to say about that?
Yeah, I know it's done. It's quite a common practice. The coverage, usually you make compromises. You're less strict on the coverage of head speed. You try to apply to the more critical passes. Yeah, it's definitely done, and there's usually a big struggle to clean it when the chip comes back. The cleaning, I can tell you from my experience, we had Tsachi maybe remembers it. It took 2 years after our silicon came back from manufacturing, more than 2 years, to approve the test program. Just to figure out why this test is failing, and then you give up and you say, okay, remove this test from the suit, and then you need to justify it and do failure analysis, and it goes on forever till you give up.
Okay.
But
the big guys,
the big guys are really, there's always a quality manager in companies like Cisco that they are the buyers of your chip, or Huawei, and they are very strict about your coverage and PPM and all of that. So you need good answers to explain what is your coverage, and because they are very sensitive, like you said at the beginning of the lecture, to to recalls and so on. So they don't understand chip design, but they understand that it has to be 100% covered.
Okay, so the last thing is IDDQ testing, and I don't know much about it, but basically it's a different way to look at how you test things. So it tests the power consumption rather than the functionality. And it can find all kinds of problems that maybe you have in different transistors and in different metals that you can't see them, or that your stuck-at faults don't cover. So the advantage is that it covers non-stuck-at faults. The test equipment is cheap, and you have a few test vectors. It's slow, and it's difficult to determine the right thresholds and so forth. But it's another thing that's discussed often. I don't know how much it's done or whatever.
You need to guarantee that you have a mode where nothing is toggling in the design. That's once you have this mode, you can do the IDDQ. You can disable all the clocks. Everything is all the clocking is controllable, and then the PLLs are not running and so on, and then you can measure your static power. That's, I think, the basic.
It shows you if you have a short, basically.
Yeah, that's the basic requirement to make sure that you don't have a big leakage or a short or, yeah.
Okay, so if you guys aren't too tired, we'll try to do the last parts pretty quick. So the next one is built-in self-test or BIST. Okay, so basically when we use this this tester, this ATE, it's expensive. We need to do what it says here. We have these stored test patterns. We have these electronics that can touch the actual chip. They stream in the pattern, then they run it out. We compare it with what we expected to get versus stored responses. It has to work really fast to get through things. It costs money as long as we're on the tester and so forth. It's hard to do it at speed, etc. So instead, what we can do is add dedicated hardware for test generation and response evaluation. It's actual hardware that's on the chip that does things for specific blocks. Memory is the biggest one that uses built-in self-test. Okay, it costs us because we have to put hardware in that does this, but it runs much faster. It can be done in the field. For example, in automotive, you need to run online BISTs all the time to see that nothing failed over time. Plus it can run at speed. So it's a very actually popular, it's getting more and more popular doing these different BISTings. So a basic architecture of a BIST is something like this. Here's our circuit under test. That's our chip, or it's not our chip, it's a block inside the chip. And we have some sort of a test generator that's pushing in the test to there. And we have some sort of a response compactor that's checking if what we got is what we thought we could get, and it's telling us if we passed or failed. Okay, so that's kind of our type of general architecture, and let's discuss a bit of how this is done. Well, okay, so just another word about this. The problem is that if we want to make patterns, we want to make a lot of patterns to test our circuit. How are we going to store them? We could store them in a ROM or in a RAM, but that's going to be really expensive. We're going to have to, if it's any size, normal size circuits, we're going to have a lot of patterns. And then we have to have this huge memory for doing it. It's pretty unfeasible unless it's something really specific that we want to test in this way. We could just have a counter, for instance, if it's a memory that just goes from 1 to N and goes through all the addresses or something like that. But that's kind of that's, first of all, I mean, it might not be the way that it checks enough randomness and so forth. And so kind of a random pattern generator would be really nice. But one of the questions is, how are we going to check what it pushes out? And that's what we have this response compactor too. So if we have the different inputs that could be, we're going to have to check them against what we thought the output was going to be. Again, that's a lot of storage, a lot of memory. So we have to do that in a smart way. So first of all, something that not all of you have heard of, unfortunately, because it's a very useful digital block, and I don't think it's taught at anywhere in university, is called an LSFR, or a linear feedback shift register. And basically, it's a pseudo-random pattern generator. So what you do is you take a shift register, and at certain points, you tap it, you take the output of some of the points, and you push them into an XOR or an XNOR gate. Okay, and what it does, it gives this thing some sort of a characteristic polynomial, so you can describe mathematically what this does. And interestingly, some of the patterns that this type of a thing makes are what are called primitive polynomials. They're these polynomials that you can only divide them by themselves or by 1. And when you get a primitive polynomial, it gives a maximum length output, which means that when you toggle through all of the states that this type of thing goes to, it goes through all of the different 2 to the n values, that 16 values that you could get in the shift register. Actually, not 16, because if we were to put 0, 0, 0, 0 at some point inside this circuit, then it would just get stuck at 0, 0, 0, 0. So it's 2 to the n minus 1. So in this thing, you can get 15 values, or you can see here that depending on where we tap it, if we tapped it on this bit or on this bit, and it also depends on if you use a XOR or an XNOR, and it depends on what seed, what your initial value is, you will toggle through the different states. And in this case, every 7, you'll get all 7 numbers of this 3-bit vector, and then it will repeat itself. So it's not really random because it repeats itself deterministically, but it gives something that looks like a random type of a generation. So it's really nice to make these kind of weird patterns, and it's a small piece of hard. What?
Quasi-random.
Yeah, pseudo-random they call it. So that's an LSFR, and it's very useful. And specifically, okay, we can to test the circuit, we can use this pseudo-random generator. We can put in LSFR and then make 2 to the power of n patterns out of with only n registers, which is really nice because if we have a 32-bit input to some sort of a multiplier or whatever, we can just use 32 registers and go through them and not go through them, one after the other, which might not show different types of faults that have to do with just a regular type of a step function between them. But how do we check that what we put in is what we wanted to happen and come out? And so that we need this response compactor. Okay, so it's called a response compactor and not a compressor. The difference being that a compactor takes whatever our vector is and changes it into something that we can use to compare, but we can't go backwards. Compression, on the other hand, it makes it something smaller, but it also keeps all the data so we can find what we had before. So if we zip a file, we can unzip it. But if we do some sort of a hash on a file, we can't figure out what the file was. So that's the difference between compaction and compression. And here, we just want to know that our test passed or failed. We don't want to, we don't need to figure out which test it was that passed or failed, for example. Okay. So what it does, the compactor reduces the response into a signature. So it goes and it does some sort of a hashing function on the response. And then we know that test A should have this type of signature and test B should have this type of signature. And the test can be really long, a lot of bits, 2 to the 32 or something like that, vectors that went through, but it only has a 32-bit response. And so we just have to save 32 bits to know it was right. So then we can store, like, say, those 32 bits instead of storing the response of each of the 2 to the 32 input vectors that went in. And the way we do it is similar to what's called cyclic redundancy check, or CRC, which is something that's done on basically any type of transmission that we do. So we have here our test generator, which is our LSFR that's making some sort of random pattern that goes through all the 2 to the n minus 1 patterns, goes into the logic, and then this comes out and it goes into another LSFR. And we know that if it goes through this LSFR, we finish the test, it's going to finish at a certain state of these 4 bits. And finishing at that certain state, it should always finish at that certain state. So all we have to do is save these 4 bits and say, okay, after we ran through all these 15 inputs, we should have this 4-bit output. And think if it's 32-bit input, we have to run through 2 to the 32 inputs, but we only have to have 32 bits to check if the output, or it's actually not even that, it can be less or more, but it's basically a many to one mapping. Now, the problem is, let's say that we ran 2 to the 32 vectors, but we only had 1 output or 2 outputs. So it would map into 4 different things. Obviously, many different tests would map into the same output response, and that's called aliasing. Okay, and that's a problem because it could be that we ran a test, there was a failure, but it still give a correct output. But the bigger the output is, the lower probability that we'll get aliasing. And usually when it comes and we have something like a 16-bit output, usually the probability will be almost 0 that we'll have this type of aliasing that will show us a false positive. So there are 2 approaches, actually. One's called a signature analyzer, which is just an LSFR that we put a 1-bit input into. Okay, but the more popular is called a multiple input signature register, or MISR, which is a parallel LFSR. It's actually what's shown here as well. So what we do is we take the inputs and we drive them into intermediate points inside the LSFR. And what that does is, so the signature analyzer means that on each output from the logic, we have an LSFR, and that costs a lot. With the MISR, we use one of these MISRs and we drive in parallel all of the outputs into it. Okay, and that will, again, we run this before making our chip or in simulation. We see what our set of tests, if we put a certain seed inside the LSFR, we know what the output will be. So all we have to do is store that output and check that the state of the MISR at the end of the run is the same as what we stored. And we don't have to store very much, so it's really good. Okay. Any questions about that? It's actually very cool. Okay. MBIST or memory BIST, that's a BIST for memories. It's a special case of a BIST in general. Memories, I think 100% of them will be checked by a BIST because you don't want it, you have a lot of bits and you have to check them all. They're not some sort of random logic that's hard to, that you have to make a specific test. You know, it's just something that has to store a 1 or a 0. So you basically add a BIST that can check it. Basically, this is the type of design. You have some sort of controller. The controller puts out an address. It puts out some sort of data and some sort of comparator. If Hanan is here, that's what you made with Tahi, right? Is Hanan here? I don't see Hanan. He was here at some point. Anyway, and it runs through all the memories, and this type of a BIST will go and check all of the different SRAMs around our circuit. Okay, but with memory BIST as well, it's there's a lot of different things about it. So there are different testing algorithms. So just to go and change address 0, address 1, address 2, address 3, and address 4, and so forth, and like say write zeros here, write ones here, and so forth, it may not be able to find all the different types of fault models. So there's a lot of research that shows different types of algorithms of how to check your memory. The most popular one is called March. March is a type of test. There are different types of March tests. So if you hear March tests, you go into the literature and see what this certain type of March test is, and it's basically the sequence you do. Let's write ones to this line, go to the next line, write checkerboard, go back to the first line, read the ones, go back to the second line, write the opposite checkerboard, go to the next line, write ones, and it's a whole type of a thing that shows that it will check if there are failures because of two cells that are next to each other, or all kinds of weird things like that. Okay.
Read after read, write after write, read after write, all that.
Exactly. There's also something called built-in self-repair, which Udi mentioned before. So in memories, because they are prone to failures because there's so many of them on the chip, and you want to make sure that they work 100%. So one of the things to do is you can, in a not too expensive way, actually add redundancy to the memory. So you add spare rows and or spare columns, and then when you run your BIST, you see that one of the one bit doesn't work, so you can remove the row that goes to that bit, and then you just target the decoder so it actually accesses a different row when you go to that address, and then you make your faulty memory actually work. So that's called redundancy, and the test that fixes it is called a built-in self-repair. And that's very common also. In most of the memory compilers, you can actually tell them, I want this SRAM to have redundancy or not have redundancy, etc. There's also logic BIST. So logic BIST is again, making a BIST, but not for a memory, but actually some sort of a logic circuit. And it's harder to do than memory, but it's something that is more and more common because the hardware that you have to put into the chip is often much cheaper than the testing that you have to run on the chip. So you try to do some sort of a logic BIST with the LSFRs and different things that we showed before. And the final part before we can finish is boundary scan, or IEEE standard 1149.1. And the question is, what about testing the board? Okay, so actually testing boards is also problematic. We need to verify that all the solder joints are good. So we need to see that the board actually connected to all of our millions of pins or thousands of pins or whatever in a good way. We need to drive the pin to 0, to a 1. We need to check that all the connections were made. We might have many chips on a board. How are we going to do this? So actually the standard way is called using a bed of nails. So you can see that this tester has all these nails, and they connect to the pins on the board, and they can check that that the pins worked, but it actually can get very complex. And once you have all kinds of BGA boards and stuff, it's basically infeasible. So that's why a long time ago, a bunch of, and the other thing is, if you want to do something that works across companies with different types of chips on the same board and so forth, you have to have some sort of standard. So the different companies got together. They made a group called the Joint Test Action Group, or JTAG, and they wrote this standard, which became IEEE 1149.1. And it's basically to write a way of building a capability of observing and controlling pins into each chip to make the board testing easier. So boundary scan is something like this. What we're going to do is we're going to build the same scan type of a structure, but instead of now going through the flip-flops in the design, they're going to go through the chips on the board. So I'm going to take my data, I'm going to drive it into one pad. It's going to shift register around all of the pins on the chip and go out into another chip on the design. And then I can, again, use this type of a shift register type of a thing to do several things. First of all, I can check that all the different connections on the board were made well. Why? Because I can go and I can put it in a certain position where I'm actually checking any of these intermediate connections, measuring if they're ones or zeros or so forth. Plus, I can check connections that go between chips, and you can do all kinds of things with this. They wrote a language called BSDL, Boundary Scan Description Language, to define the tests that actually do this type of a thing. But in the end, it helps me test my board in an electrical type of a way without going and using that type of bed of nails. So basically, every chip you make, you have to implement this boundary scan on it. You also have this thing called a tap controller, which is the test access port. And each chip will have 4 pins that are called TCK, TMS, TDI, TDO, and TRST. So that's, one of them is the clock that shifts this stuff along. One of them is the test mode select. So it puts it into this shifting thing instead of their operational mode of being inputs and outputs to the regular inputs and outputs. Serial test data in and serial test data out. That's going into the chip and out from the chip. And reset, you can optionally also do reset through it. Inside this, what you would have in your chip is a wrapper that connects all your IOs together. Okay, so you have these inside the IOs. You have to have a register. I will ask Udi and Tzachi, are the registers inside the IO cell itself, or is it a separate register that connects to the IO?
It's separate.
Okay. I was wondering that because anyway, but you have to have a register that's connected to, like, a scan, basically adding scannability to the IO cell. You have a bypass register that if you don't want to test this chip, it can go from TDI to DDO and bypass it. An instruction register, you store the instruction of what you actually want to do, because again, you're not just running a scan chain through this. You may be doing all kinds of things like passing things in between and doing things inside. Okay, device ID register, that's if you want to read out what the identification of the chip is, you can do it through this JTAG. And design specific registers, those are things that people can add to do all kinds of debug internally. And then you have 3 types of tests, or more, there are more, but 3 important ones are X test, that's the interconnect between devices. So you would drive some sort of interconnect, some sort of vector through here, then put it back into the regular mode. So these guys would be passing their signals to somebody else on the board. Then you would capture them on a different chip and then drive them out and see if you got the right thing, and it will test the interconnection between the chips. Bypass, again, is if you want to not check this chip because maybe you haven't put it on the board yet, or maybe in a certain configuration of the board you don't have it, I guess. I'm not sure exactly. Maybe I said stupid things. Tzachi, fix me if I made a mistake there. And in test is the internal logic of a chip. So that's actually the backdoor that usually is added to the chip to do all kinds of debug stuff, because we already have this type of a scan chain and this type of a connection that's a standard that we have on our chip, we have on our system. So why not use it for doing all kinds of other things inside? Tzachi, anything to add there?
No.
Okay. So actually, that's all I had to say. I have several of the references I used. I used a lot more. Questions? Are all of you guys who haven't been talking still awake? The fact that you're not answering means that you're probably not there. Good. Okay, so that was, now you know something about skin. All right.
I can tell you it's a big pain.